Okay, so hello, I'm Alexander Wagner from the University of Hohenheim, and welcome to the presentation of my paper on the effects of absumption for XCS with continuous valid inputs, or more short, how to handle overgenerality in XCSR, which is the underlying research question of this paper. So at first, I will give you a short introduction to the issue of overgeneralization in XCS and XCSR. Then I will introduce you to the newly designed overgeneral handling approaches for the XCSR, which is the XCS for the continuous valid inputs. And then I will report the results we obtained in experiments in single and multi-step problems. So at first, introduction for the problem in overgeneralization in XCSR and XCS. So what is overgenerality? So in XCS, if a single classifier matches multiple incompatible niches, this classifier is regarded as overgeneral. And what does incompatible niches mean? It means that these niches belong to different data set or data types, and they need different actions to be correctly predicted. So in case the classifier population contains overgeneral classifiers, this overgenerality will result in incorrect classifications or inappropriate action selection. So in the end, it will lead to a reduction of the overall learning performance, and therefore it will also lead to an incorrect representation of the underlying problem of the environment, which will be created inside the classifier population. Therefore, if you want to use the classifier population, for example, for explained by AI purposes, the representation will be incorrect. So, and also it's interesting what are possible causes of overgenerality. This depends on the type of problems which XCS is used for. For example, in single-step problems, non-uniform sampling or unrecognized niches are associated with the problem of overgenerality. And these two problem types or these causes are also related to the problem of unbalanced data sets. And like in unbalanced data sets, for the majority class, the overgeneral classifiers will form. In multi-step problems, overgenerality is associated with sparse reward signals and long action chains, which make it hard for the XCS to distinguish the different payoff levels in the multi-step problems. So to get a more intuitive idea of the differences between overgeneralization in binary problem domains and in the continuous value problem domains, here are two visualizations. In the binary problem domains, classifiers are, or the dimension of a classifier is represented by 3 possible values, and the generalization is represented by the hash sign, which represents 0, 1, or can stand for 0 and 1. And therefore, in each dimension, you have two possibilities to get the correct, more specific classifier. And there you can either set these hash signs to more specific versions, and then you will get the correct version. In the continuous value problem domains, the classifiers are, for example, represented by hyperrectangles. And therefore, in each dimension, they are defined by interval predicates. And here, an overgeneral condition, therefore, here in this case, for the Mario pixel art, there it covers multiple different niches as it covers different colors. Therefore, in theory, these interval predicates there are infinite variations for these interval predicates per dimension. And therefore, the complexity in the continuous value problem domains is substantially increased to find the correct, more specific classifier. So back to the research question, how to handle overgenerality in XCSR. This research question came up as we were doing research with XCS in multi-step environments. And when we were looking for a solution, we found that until now, there's no approach present for XCSR or for the continuous value problem domains to handle overgenerality. But there are two approaches present for the traditional XCS for binary problem domains. These two approaches are the absumption mechanism, which was proposed by Liu et al. In 2019, and the specify operator proposed by Lanzi in 1997. And as these two approaches were designed for the traditional XCS, they are not directly transferable to the continuous web problem domains, but the basic idea can be transferred, and therefore in our paper we adapted these two mechanisms or these two approaches to design a new over-generality handling for the continuous web problem domains. And therefore we designed two approaches. One is based on the absumption mechanism and one is based on the specify operator. So now to the two newly designed over-generated handling approaches. As I said before, these two basic approaches for the traditional XCS are not directly transferable, and especially the specialization techniques or strategies which create the new specialized classifiers in each time specialized classifiers for the over-general classifiers are not directly transferable to the continuous web problem domains, as it has been shown on the previous slide, because of the different definitions of generality in the binary problem domain and in the continuous web problem domains. But the identification techniques, they are transferable, and in absumption, this identification is based on the idea that overgenerals matches multiple or matches these incompatible niches, and therefore if overgeneral matches positive, or if the overgeneral receives positive and negative reward values, this classifier is regarded as overgeneral, and then it will be decomposed into more specialized classifiers, and the number that it is decomposed is defined by the numerosity of the overgeneral classifier. And absumption uses a direct approach to detect overgeneral classifiers, but it's only applicable in single-step problems. In specify, the detection is based on the increased prediction error of overgenerals, and there the overgenerality is detected in case when the action set or the prediction error of the action sets is higher to a certain level or is above a certain level of the average prediction error in the population, and then a prediction error proportionate selection is performed, and for this selected classifier one specialized variant is created. And in specify there only an indirect detection is performed, but it works in single and multi-step environments or single multi-step problems. So to adapt over-generality handling or to create over-generality handling for continuous web problem domains, we designed new classifier specialization strategies. And these strategies are the new condition specialization, the NCS, and the inside condition specialization, the ICS strategy. Both strategies have in common that they create or that they copy the attribute values of the identified overgeneral classifier to the newly created specialized versions, except the numerosity, which is set to 1, and the experience, which is set to 0. In the mode of operation of the new condition specialization is as follows. The newly generated specialization conditions are randomly generated, similar to the covering operation in XCS or XCSR. And they use for the random generation, the center point of the overgeneral classifier condition is used. Also, the spread of the specialized condition has to be smaller compared to the original overgeneral, to the spread of the original overgeneral condition. Therefore, the newly generated specialized conditions must contain the center point and have smaller spreads compared to the overgeneral. This technique is fast as it is random, but it does not guarantee that the specialized conditions are inside the original overgeneral condition as it is shown here in the visualization. Therefore, to ensure that the specialized conditions are inside the overgeneral classifier condition, we designed the inside condition specialization, the ICS, which adds an additional constraints to NCS, and therefore it extends the NCS strategy. And there, the newly generated specialized conditions must be also within the overgeneral classifier, as it is shown here in the visualization there. So it's also randomly generated. The spreads are smaller, but additionally, the specialized conditions have to be within the original overgeneral. Also, as I said before, that assumption is not applicable in multi-step environments. We also designed a new identification strategies for overgenerals for Absumption, which enables the application of Absumption in multi-step problems, and that's the prediction deviation variance. This identification strategy is based on the idea or based on the increased prediction oscillation of overgenerals, or the prediction oscillation of the overgenerals. So in multi-step problems, the environmental niches are defined by similar payoff levels. And as the definition of overgenerals says, the overgenerals cover multiple or different environmental niches, and therefore they cover different payoff levels. So, for example, if an overgeneral classifier covers two environmental niches, one with a lower payoff level and one with a certain upper payoff level, the prediction value will oscillate between these payoff levels. So this oscillation can be detected, and therefore to detect this oscillation, this identification strategy tracks the variance of the deviations of the classifier prediction and the payoffs the system receives. And this is tracked for all classifiers in the classifier population. And in case if the variance of a classifier is twice the average variance in the population, this classifier is then regarded as overgeneral. So that much to the new techniques. Now to the experiments in the single multi-step problems. So the experimental setup we use to evaluate our newly designed approaches or in other adaptations is as follows. We conducted experiments in 3 single-step toy problems, in 3 agricultural datasets, reward agricultural datasets, and 2 multi-step environments. We also tracked different metrics for the evaluation. The first one was the reward the system received, and the system error, which is the error between the system prediction of all the classifiers and the system prediction and the reward received. Then the population size and the generality, which means which is the average volume of the classifiers in the population. And especially for the multi-step environments, there we track the steps to go. We performed the experiments for 30 repetitions, and we also performed statistical analysis. So we performed an ANOVA plus a 2K HST post-hoc test in case homoscedasticity was given. And in otherwise, we performed a Welch ANOVA and a Games-Howell test, post-hoc test. So the experiments in the single-step toy problems, there we performed, or both OGH approaches utilized the NCS strategy for specialization. And there we obtained these results. Here the Absumption-based OGH performed best or outperformed the other configurations, as it's also shown in the exemplary results plots for the Mario pixel art, which is also here in percentage written. So in the Absumption-based OGH improved the reward by 4.7% and reduced the system error by 18.1%. And here the Absumption-based OGH is defined or represented by the blue characters. Specify also improved the led to improvements compared to standard XCS. It's also represented by the yellow characters, but to a lesser extent compared to the Absumption-based OGH. In the other environments we used there, both OGH approaches performed similar to the standard XCSR. It also has to be noted that both approaches led to an increase of the population size. In the agricultural datasets, both OGH approaches use the ICS specialization strategy. And here we have exemplary results for one dataset. It's the paddy leaf dataset. And here also the absumption-based OGH led to the fastest learning and also led to the highest results or outperformed the other configurations. And once again, Specify also led to improved results, but it's only Specify only led to improved results in this special data set. So all the overall improvements of OGH were that of the absumption-based OGH were that it improved the reward by 20.3% in the maximum case, and the system error was reduced by 45.3% in maximum case, and also the median was by 40.9%. So OGH or the absumption-based OGH led to the highest improvements. In case of the population size, there was also an increase due to the Specify-based OGH. But for the absumption-based OGH, there was mostly no increase. Now, last but not least, the results we obtained for the multi-step problems. Here in this experiment, both OGH approaches also use the ICS specialization strategy. And for the first time, the absumption-based OGH applied the prediction deviation variance identification. Here, also in the exemplary results for a special configuration of the grid world we used with a step size of 0.05, the absumption-based OGH reduced the steps to go the fastest and also led to outperform the other configurations. And once again, Specify also was superior compared to the standard XCS, but to a lesser extent compared to the absumption-based OGH. Here, in the overall results of our experiments in the multi-step problems, the absumption-based OGH led to a reduction of 31.5% at max of the steps to go. And the system error was also reduced by 48.3%. Here, in the multi-step problems, both approaches led to an increase in the population size. So what are the implications for that we get from these experiment results we obtained? So with OGH, significant improvements, especially in the studied agriculture datasets and the multi-step problems are possible, especially when the absumption-based OGH is used. In the toy problems, only in one toy problem improvements were achieved, and this was the Mari environment. In the other two toy problems, namely the 6 remultiplexer and the checkerboard problems with 3 dimensions and 3 divisions per dimensions, no improvements were achieved. So possibly the equally sized niches with strict boundaries, which are especially present in these two toy problems, seem to be a challenge for OGH. And also, furthermore, we saw that in OGH, the increased that OGH leads to increases in generality in the CPP33. And if you keep in mind that the learning performance was similar to the standard XCS, it seems like OGH facilitates the generation of maximal general classifiers. To 1.2, the population size. The causes for the increase in population size, maybe two possible causes. First, we deliberately create more than one specialized classifier for a single overgeneral, and also due to the random generation of the newly specialized conditions or classifiers variants, there are a lot of over-specific classifiers will be created, and these transient rules need time to be deleted from the population. So now the conclusion. So we adapted, or we designed two overgenerated handling approaches, one based on the absumption mechanism and one based on the specify operator, and we adapted them to the continuous well problem domains. And this was done by introducing two new specialization strategies for the continuous well problem domains. To enable the application of absumption, we also designed a new identification strategy which enables the application to multi-step problems. And in the experiments we performed or we conducted, there were significant improvements, and especially in the examined agricultural data sets and multi-step problems. So the overgenerality handling provides a promising means to deal with the overgenerality issue in XCSR. So to our future work, this future work will be directed on a more focused specialization pressure, and this should be enabled by either the realization of a more precise localization of the incompatible niches, or a more systematic decomposition of the overgeneral classifiers. So this is the end of my presentation. If there are some questions, I will also contact details, and I'm open for questions. And thank you for your attention.
Thanks for your presentation, Alexander. So we have 3 minutes for questions.
Hey, Alex, great talk for the start. So, do you allow me to ask you some nice questions?
I will allow you, yes.
Just one for the start. So, you mentioned that you did try that out on agriculture data sets. Are with some general open source data sets, or is this from a customer of yours?
No, that's open source data sets. It's from the Kaggle and UCI repository.
How do you compare to other state-of-the-art methods on these data sets, or did you only take a look at learning classifier systems?
I only did compared to the to learning classifier systems. I did not compare it to the other algorithms there.
So in which direction will you go? Will you then try out other stuff from Tony, like interpolation, or do you want to go more into application?
Yeah, it's also it's directed to the application. Maybe I will use the interpolation techniques if they work correctly or efficiently, I would say. And yeah, it's more directed to the application.
Okay, so do you have a first customer already?
No, not until now. It's
okay. So first step is in theory, right?
Yes.
So
it's theoretical, but also directed to application.
Okay, but generally interesting. So thanks once more. So you will get your shot at with nice questions at me after my talk.
Okay.
Okay. Actually, I have a follow-up question. I do believe, just a side comment, I do believe it's important it's nice to compare with the other evolutionary approaches, but at this stage, I think we should target the other methods also, but that can be addressed in future work. There is something that I was wondering, and maybe this is a stupid question, but I'll make it anyway. You have slightly different performances in different data sets, and that is expectable, of course. But were you able to figure out why you are having different performances? Is there something in the data sets that relates immediately with these different performance, and is this predictable due to the characteristics of the data set?
That's a good question. There I didn't figure out a direct characteristic of the dataset which is related to a high increase or to a lower increase. So I need to do more tests on different datasets to get a systematic of the improvements or what's causing the better performance or low performance. So it's also future work to do more different datasets.
Okay. Okay.